Hello, everybody. So let's start with a new session, so related on small modular reactor design within virtual twin experiences. So first of all, let me introduce myself. So I'm Olivier Audelan, part of Dassault Systèmes, working for the Katia brand. Since 21 years now, I'm in charge of technical activities on infrastructure and buildings. And I'm really pleased to co-present that session with my colleagues.
Okay, hello everyone. So my name is Clément Pozzo. I joined Dassault recently. I was a structural engineering prior to joining Dassault. I'm working on an infrastructure projects within the industry, and it's good to be here.
Yes, so hello everybody. So Achimi Moudi. I'm part also of the Katia brand. I'm a system engineer and a Katia consultant for system engineering and all model-based system engineering.
Thank you, guys. So let's continue. So back to the main topic of that session. First of all, so we will do a short recap of what has been explained yesterday by our colleagues from Dassault with our partners from Systèmes regarding how to speed up SMR with MBSE. So just a quick recap, first of all, why do we need a virtual twin? Because simply we have to face some quite important challenges from an architecture standpoint. What is the right system architecture for my project, for my product, for my process, for my facility, time to market, what can I do to be the first on my market regarding life cycle? How can I take into consideration the complete life cycle of my facility during the design phase? For all that is related to modularity and product line management, how can I ensure that my modular reactor will be manufactured and delivered efficiently? And last but not least, safety and licensing. Can I really secure the regularity process from standard design approval to license to operate? And this is for those reasons that we definitely think that virtual twins are key to address those challenges. And I would say it's not only a matter of one virtual twin. We will have to deal with virtual twins. Virtual twin of the product, of the process, of the facility, virtual twin of the supply network, etc. This is really what we want to aggregate on the 3D Experience platform. And to do so, what is really important for us is to believe on a framework, a model-based system engineering framework that will allow us, in fact, to define, if I may say, the skeleton of those virtual twins. We need to clearly define, standardize processes in order to be able to apply them on the different layer we would like to manage on our virtual twin. And by doing so, by defining systems architecture, by refining and defining requirements, we will have the capability to define efficiently the different breakdown structure. By defining the breakdown structure, being able as well to define the right systems. I'm not talking about designing, I'm really thinking about defining the systems, and zone per zone, being able as well to define all interfaces that are crucial for those projects. Because it's not only defining a product, a process, a facility, but if we have to engage on modularity, we need as well to clearly define accurately those interfaces in accordance with some new requirements that are not only related to engineering, procurement, and construction. We need to think differently the way we manage those requirements. This is the reason why, in fact, the model-based systems engineering is definitely important for us in order to be able to define accurately that backbone of virtual twin. And as well, this is really the purpose of the session presented yesterday by Xavier that is on the room with a system in order to collaborate with engineering company in order to integrate on our model-based system engineering framework templates, best practices coming from that engineering company. But now let's have a look on the virtual twin. So I won't explain you, in fact, how to define virtual twin, but you can see like that an overview of the process we are addressing, and then we will deep dive on two main use cases we would like to introduce today. But at least like that, the purpose is really based on the systems engineering to be able to define the site on its environment. It's really crucial to identify as well the external interfaces related to that environment, so meaning linear infrastructure, industrial infrastructure, to take into account if I need to deal with hydrogen, if I need to optimize my supply chain, and so on and so forth. I not only have to think about my site by itself, but my site integrated on the environment. And then being able, based on that virtual twin and all that model-based system engineering approach, to collaborate in between all disciplines, from civil till general installation, in order to define, design, and being able to prepare efficiently all the construction and operation activities. So this is really the purpose of that virtual twin that we are sharing with you today. So now let's focus on two main use cases. So the first one is, we called it build virtual twin of SMR, but we will definitely focus on the civil design, and so Clément will take the lead. And then we will have a look to a new constraint that is quite key on that market, how to be able to adapt an existing product to a new market. And this is where we will see the power of the model-based systems engineering in order to be able to analyze, identify what are the potential impact of a new requirement on existing systems, and then being able to adapt or to define, design variants of an existing product. So let's start with the virtual twin of the SMR. And as I told you, the purpose is not to deep dive on all the topic. Yesterday, you had a look on MBSE and then till the process flow diagram, the PNID, etc. So today we will focus on civil, and we will come back to the MBSE for the second use case. But now, Clément, stage is yours.
Yeah. Thank you, Olivier. So let's talk a little bit about structural engineering now. We're going to talk about multi-scale and all phases of projects. So traditional structural engineering is everyone working on bits and pieces and then assembling those, bringing all pieces of puzzles and trying to map it out. And that causes multiple issues, is that we're constantly having to start back from scratch because we have all these conflicts, these clashes. When we're talking about such a high security and high complexity field as nuclear engineering, we're firm believers at Dassault Systems that the only way to start a structural engineering project is through model-based system engineering, as Olivier was talking about. So when we're doing this model-based system engineering, we're going to be mapping our objects. So here we have the flooring, intertwined with all the different installations, with the pumps and whatnot. When we're looking at these objects that are going to be into systems and diving into the subsystems, we then can run some deep dive analysis on certain objects or certain systems, and the repercussions will be instantly instigated within the system engineering. So we don't have to start back from scratch every single time we tweak something, tweak an object, tweak a system. So let's dive into something more concrete, and that's a structural engineering joke. Here we have the reactor core, the cylinder, the concrete cylinder that is one system of our asset. We're going to be analyzing different scenarios. Okay, this is precast modules. We're going to be prefabricating them, lowering them into place, and that will cause a certain amount of issues. We're going to weigh the pros and cons. Maybe another scenario would be pouring the concrete in and different phases of concrete pours. And that's going to bring up another set of issues. For instance, durability-wise, the exothermal reaction within concrete hydration will cause heat piling up within the concrete pour phase, and we're possibly going to get concrete pathology in the midterm, which is something very scary that we don't want to be talking about in civil engineering, of course. So here, we chose the safer version, the precast element. This was one example of scenarios we can run to then have repercussions on our model-based system engineering. Here is another example. So this is piping, but once again, we're talking about multi-scale, multi-physics simulations and how everything is intertwined. Here, we have fluid, water, flowing through this, this elbow here. Say this installation is on a steel frame structure, and we have this friction, creating heat, also creating vibrations within our system. Maybe we need to look into our steel frame structure. We may be inducing some extra loads and having to deal with fatigue in midterm within our structure. Another scary thing that we don't want to happen. So maybe we're going to, well, fix this issue with turning this elbow from 90 degrees to 45. This will have repercussions on our plant, on our pumps, but maybe on our beams, on our flooring. So that's what's great about model-based system engineering, is that we're not starting back from scratch. We're just running iterations. We're fine-tuning our system. We're not having to scrape the plate, start back from scratch. We're building on. So that was a dive from macro level, which is model-based system engineering. We went towards the human scale, so a beam, a pipe, a post, a precast element. But we could even imagine diving deeper into the micro scale. For instance, that issue we were talking about earlier of exothermal reaction within concrete. Well, maybe we could have found other ways to cope with it. Maybe tweaking the formula, the concrete formula, lowering the amount of Portland cement, going down to the micro scale and figuring out what's happening there. So all that being said, macro is model-based system engineering, and then we're diving into a multi-scale, multi-physic analysis to try to fine-tune our system. And that is true for design, and then we've established our single source of truth, and the handover will be flawless towards building, towards operation and maintenance, all over to decommissioning. And that's what we strive on achieving within Dassault Systems and infrastructure work in a high complexity environment such as nuclear. Yeah. So, Hatim?
Yeah. Thank you. Thank you, Clément. So let's continue with the second use case. In fact, this is what I was talking about: how to adapt an existing SMR to a new market, and to do so, we need to think a bit differently. Meaning, we need to think about having a configurable product that we can adapt regarding customers, regulation needs, etc. What is important is then being able to configure that product regarding customer need or a dedicated regulation, and then being able to start a serialized production based on the location, and potentially as well based on constraint regarding the local supply chain, etc., etc. Hatim, could you tell us, in fact, how MBSC can help on that approach, please?
Yes, of course, Olivier. So as we see here, we have different, let's call them, facets of our system, starting by the specification here, which contains all our requirements that can come from either customer or that can come from other stakeholders within the same company. Okay, and we start by doing some what we call system architecture, which is the model-based system engineering phase, and this will give us the, let's call it, the high-level specification for our system. This is where we will define the high-level interfaces, the flows, the type of those flows, what we exchange with other systems. Okay, so we break the silos, we work together to define this architecture, and this, let's call it, this is the switch where we go from systems engineering as an architecture to go directly to define the product itself. Okay, so we have actually a little demo scenario that where we will explain all of this, and we will add on top of this what we call variability management. Okay, so our systems, it has different variations and it evolves with time. Okay, and depending on where it will be sold, this system, we can manage this variability. So it's basically the governance of our system. Okay. So we have a little scenario here where we will receive a new requirement that will tell us, okay, so in this market we have new regulations and we want to reuse our system. So how can I do? Okay, so the important thing is that systems engineering or model-based systems engineering is something iterative. So there is nothing wrong in coming here and going back, okay, to correct something. This is the whole purpose of systems engineering. Okay, so we will go directly to do some impact analysis, so to see, okay, we have a new need that is coming here, and what this requirement will impact in my system. So this is given the fact that I already did some traceability, of course. So if we do system engineering, we need to trace everything we define, okay, through all the life cycle of the system. Okay, so I will see the impact analysis, and here, when I see all the impacted elements, I will define some system variations that will depend on the regulation that is coming in, okay? And afterwards, we will see that all the elements that are impacted will be modified and revised. So we create new revisions, okay? And we put on chaque element, okay, so this element will be available for this type of market starting from this evolution, for example, okay? So we have a small video that showcases this. So I call this video MBSE to plant modeling journey. So it's basically a journey of all the system engineers. So we have here our traceability scope. So we use the power of the 3D experience platform as a federator of all the models to create this traceability. We have the information about the coverage. Okay, we can see that we need to do some more traceability, for example. And here, based on our new regulation requirement, we can see that, for example, in this system, that the heat exchanger, we will not be able to include it in our architecture if we want, for example, let's say, to sell to Japan, for example, okay? And we will see this afterwards. So I have all the impact analysis straightforward to the 3D. So I can highlight everything my new requirement will impact through all the life cycle of the system. So from system architecture to logical part to the PFD, which is the schematics of the fluid system, directly to the 3D. And we can see it's the same architecture coming, for example, from CATIA Magic, where we do our MBSE. Okay? So the next part of everything, of all of this, sorry, is that we will need our variation of the system. We will need it to impact all these phases. Okay, so starting from the requirement, we need to eliminate this logical part in the system architecture, in the schematics, in the 3D, everywhere, okay, based on this specific configuration for this specific market. So this is what I do here. I have a configuration coming in from the 3D experience platform. I'm in CATIA Magic. So I apply, for example, for Japan, okay, so I have my heat exchanger that will just disappear once I apply my configuration. So this is what I do. I transform my model. So this is where we go from a 150% model, which includes everything, to a 100% model, which will be implemented in that specific market. Okay? And here, before I use the variation, here I will use the evolution. Okay? I will say, okay, my heat exchanger, it will be available starting evolution C of my system, but in the first one, the first version, let's call it, it will not be available. So this will help us to reuse our system. So let's say, okay, for Japan, this is our new version. We have the heat exchanger, but we don't need this based on the regulation. We don't need it. So I will just put the first one in the context of my traceability, and based on that, everything will be filtered, and we will not have our heat exchanger. So here, just a small update of my traceability scope. And if I go to my coverage, we can already see here that we have no heat exchanger. You can see the update right there in the bottom right. Okay? So just double click, impact analysis, and I see everything impacted here. And now the modifications need to be propagated also onto the product, the 3D part of the product. So directly from the 3D experience platform, I can continue my work by opening the 3D we are seeing here to do these modifications about this new configuration. Okay? So this is basically it. Thank you for listening.
Thank you. Thank you, Atim. So let's continue with typically what Atim was mentioning. So regarding the filtering of the, let's say, of the system design by itself. So we did it at the multi-system architecture level. Now let's deep dive on the system itself, unitary, from a unitary standpoint. So you can see that. So as said by Atim, everything has been filtered. So let's open now. Maybe I can speed up a bit. I don't know how to do it. I don't want to do a mistake anyhow. Let's see that when we are opening, in fact, the 3D data. So you remember the site we shown some minutes ago. So in fact now, if we are opening the PFD and as well my site, by doing an analysis, we will see that our process flow diagram has been filtered already, and the 3D has been filtered as well. So it means that, like that, by doing configuration management at a higher level, then you will be able to cascade all this filtering till the system design by itself. And again, we did not modify the, let's say, the location of the site, but this is where, in fact, by playing with a filtered site, then you could position it on another location, etc., to do some analysis, geology analysis. That is key, because before implementing a site somewhere, you need to do some geology analysis in order to take that into consideration. On your definition. So you see like that by doing a consistency check in between my PFD and my 3D, I'm fully aligned regarding the configuration I would like to apply for Japan. What is as well interesting, it's all my requirements as well connected to that system design. So if I still have to continue the design of that system, of that cooling system, I will do it in the context of Japanese requirements, so the one that we selected for the configuration. And what is as well interesting, it's we shown, in fact, the PFD and the 3D cooling system, but for the PNID, it will be the same. So again, all the system definition has been filtered in accordance with the configuration, the Japanese configuration we were willing to apply. And it's not only a purpose of pure design, because why are we building a virtual twin? We are building a virtual twin in order for us to be able to simulate at any stage of the life cycle of our asset. So what is as well important, it's we will have as well the capability to simulate the behavior of that cooling system, or let's say of that filtered cooling system, configured cooling system with Daimola, in order to validate that the system, on the way it has been designed, is fully compliant with the requirements we are willing to fulfill for that system. So this is something that is really key on that topic. It's not only modeling, it's modeling and simulating in order to be able to validate the system definition based on requirements. And then to be able to ensure traceability, because if we discover that during the simulation of the process we have some issues, we will do it in the context of requirements. So being able to close the loop in between the simulation engineer, the process engineer, based on requirements management as well. And again, the traceability is key. This is where, if I need to reuse that module on another location, I will fully understand the reasons why I had to apply that modification based on that simulation at that time of the project definition. So you see the link now with Modelica, that is the simulation language that we are using to do the process simulation. So having the direct link in between any kind of schematics and that Modelica language in order to perform the process simulation. So that simulation model is as well configured. So again, I have the full configuration for all my systems. We are running soon out of time, so I will just speed up a bit the video if I can. Okay, just to show you. So you see, in fact, the simulation engineer has the capability to retrieve the information coming from my PNID. So by information, I mean all the equipments, all the functional characteristics of those equipments, and then the simulation engineer has just to add his own inputs in order to run the simulation. So in that case, it's static simulation, but we could do dynamic simulation, meaning by taking into account as well some real-time data information related to the weather or related to the operations as well, in order to perform such kind of simulation. So it's time to close the session. Thanks a lot for being with me.
Thank you.
Many thanks for you guys to be with us. So keep in mind the MBSE framework is really key for us to define the virtual twin of an SMR and allowing us then to manage the concurrent engineering for all disciplines to ensure a digital continuity, an entire traceability from the multi-systems architecture till the requirement, till the system design, and as well until the operation afterwards, because the purpose is not to build, let's say, a virtual twin of engineering, it's to connect the virtual twin of engineering to the virtual twin of operations, in order as well to do a loop, being able to capitalize and reuse based on operational feedbacks in order to improve, to update engineering of SMR. So thank you very much for your time. I hope it was clear, and if you have some questions, do not hesitate. We will be pleased to answer to them.
Thank you.